Hello, everyone. I'm Kirsten Wakefield, a stakeholder engagement specialist for Maricos, and together with Janet Reamer at the Mid-Atlantic Regional Council on the Ocean, we co-coordinate MACAN, the Mid-Atlantic Coastal Acidification Network. MACAN is a network of researchers, tribal, federal, and state agency representatives, non-governmental organizations, and industry members working together to coordinate regional acidification monitoring and research to better prepare our coastal communities for changing ocean conditions. Today, we're really excited to host Pierre St-Laurent from the Virginia Institute of Marine Science for an interactive demonstration on the new digital atlas for physical and biogeochemical conditions in Chesapeake Bay. We'll have a firsthand look at how local stakeholders, managers, students, and researchers can mine 4 decades of information about carbonate chemistry, biogeochemistry, and hydrodynamics to create new visualizations with software programs like Python and QGIS. But before we get to Pierre's presentation, just a quick look at our upcoming webinar series. Our final webinar of 2024 will be held in November, the date's still being determined, but it will feature the projects of our current MACAN fellows and contractors, Edith Mari, Nicole Ruiz, and Teresa Swemmer. We'll send out registration information soon via our constant contact listserv, and also it will be available on our website at midacan.org. So keep an eye out for that webinar coming up. And now today I'd like to give a warm welcome to Pierre. Pierre received his PhD in oceanography from the University of Quebec before migrating to Virginia, and his research interests evolve around the oceanography of coastal waters. He works closely with Margie Friedrichs, whose research focuses on modeling long-term historical and future changes in hypoxia and coastal acidification, as well as forecasting short-term hypoxia and acidification metrics for the Bay. Through Margie and Pierre's ongoing collaborative work with Chesapeake Bay program managers, fishermen, and aquaculture industry members, they continue to work to make their science relevant for stakeholders. So as you listen to today's webinar, just a note that all participants will be muted. So please submit your questions about the digital atlas in the Q&A box at the bottom of your screen. We'll have about 15 minutes for Q&A at the end. And also just to note that this webinar is being recorded, and the recordings will be available on our website at midacan.org. So with that, I'll turn this webinar over to Pierre to hear more about the digital atlas and its real-world applications.
Thank you, Kirsten. I appreciate it. Great introduction. I liked it. All right. I assume that you can see my screen at this point. Okay. So I will begin by giving an overview of the digital atlas, and then I have a bunch of real-life examples of how the atlas can be used. Here on the left, I'm listing 3 typical questions that you could get from a graduate student. Which month of the year has the most wind waves in the Chesapeake Bay? Is the direction of the dominant winds shifting between seasons? And where is carbonate chemistry appropriate for calcification? And until recently, the kind of answers I would get to questions like this would be, well, the information is spread across these 3 papers. Let me send you the PDF. Sometimes I would recommend to download monitoring data and analyze it to get the answer. And sometimes I would promise to try to create a few figures and get them by next week. If you're on the receiving end of these answers, it's never quite satisfying. Ideally, you would like to have a reference that answers the questions on the left without having to involve anybody. And we can ask ourselves, in 2024, shouldn't there be a reference that address the 3 questions on the left? And I took a tour of the internet, and there are tons of resources about the Chesapeake Bay, lots of information, but all of them tend to focus on slightly different topics in such a way that if you go through all these resources on that slide, none of them really address the 3 questions I listed previously. So I got the impression that there was a gap, and I asked myself, is there something I could do quickly using material I already have in hand to try to fill in that gap? And so what I had was about 4 decades of model results ranging from 1985 to 2023. And that was about 2.5 terabytes of information. Nobody wants to download 1 terabyte of information. And so I look for ways to distill this information in a package that would be small enough for anybody to download and would be reasonably quick to download. So to do that, I decided to focus on the surface and bottom of the Chesapeake Bay. I condensed all the information about the 4 decades into 12 months of the year. So I'm only looking at the seasonal cycle on average over this 4-decade period. And then I made all the information available on a very simple longitude-latitude grid of moderate resolution. And by doing all that, I was able to squeeze this information into about 114 megabytes in size, something that you can download in a few seconds with a Wi-Fi connection. So we took that product and we archived it on the CNO repository, which is free, it's public. But for the purpose of this presentation, what I did is I created the link at the bottom. So it's nordet.net/MACAN 2024. If you go to this address, you will get not only the link to the atlas, but you will also get all the materials that I'm presenting today, the NetCDF file, the scripts, all of that is there at nordet.net/MACAN 2024. So a few words about what the atlas includes and does not include. So there's a total of 27 variables, and that ranges from topography, the hydrodynamics, up to biogeochemistry and carbonate chemistry. So there's a lot of information, but it's also worth saying what the atlas is not. The atlas is based on model results, not on measurements. We do use a lot of measurements when we create the inputs of the model, when we calibrate and evaluate the model, but the atlas is not about measurements. It's mostly model results. And the other thing to keep in mind is what I said earlier. Even though the atlas is based on a simulation of 85 to 2023, because of the constraint of space, I'm only showing the seasonal cycle average over this 4-decade period. There have been people who have been asking to at least include some metrics of how things have changed between 1985 and 2023. And I'm planning in future versions to include some time series to illustrate this variability. So we provide the information in the atlas in 2 different ways. First, there is a PDF document that I call the documentation. And then there's a NetCDF archive with georeference raster layers. So 2 different ways in which we provide the information. So first I'll look through the documentation rapidly. So I have it here. I assume that you're seeing a PDF document saying documentation right now?
Yes, Pierre.
Okay, sorry. So on the left, you have the table of contents. And so it begins with a short introduction, giving context for the atlas. Then there's a table of all the variables that are included as well as their units. Then there are some notes. How did each of these variables were calculated? And then I decided to include ready-made visualization for each of the variables included in the atlas. So the idea is that you don't always have to create your own figures. There will already be something readily available for a user. It's about 45 pages of figures. Basically, I go through each variable, bottom and surface, and they all have pretty much the same structure, and it looks like this. So the idea was to have the full seasonal cycle just in one figure. That's why I'm showing January, March, May, July, September, and November. And all of these months share the same color scale so that you can just in one glance get an idea of how things change across seasons. So in this particular example, what I'm showing is potential temperature at the surface. So yeah, it's about 45 pages of images. And then once you're done with the images, there are short examples of usage. Then there's a section giving reference information about the numerical model that was used to create the atlas. And then I used, I think it was 2.6 million of data points to evaluate the model skill during the period 1985 to 2023. So I used all the monitoring program that I could get my hand on from 85 to 2023. And then I created scatter plots for each variable one by one. And the idea was that someone could look at this evaluation and decide whether the model is doing a good job, if it's doing fine enough for their purpose, or if it's not satisfying. And the model does have variable skill depending on which variable you're looking at. So it's something that you can look at and make your own mind about it. And that's it for the documentation, acknowledgements, and references. Going back to the presentation. So as I said, there's two ways we present information, and then the second way, it's this NetCDF archive. And now I'll be using 4 different tools to interact with this NetCDF archive: QGIS, Python, R, and then Matlab. So QGIS is particularly useful if you want a quick visualization, if you want to do overlays. So I will give a quick example of that. So you go to Layer, Add Layer, Raster Layer. And here I'm grabbing my own copy of the NetCDF archive. So you see here it has the .nc extension. Next, I select a specific variable within the atlas. So you see the list of all the variables that are available. So I will be selecting one in particular, alkalinity at the bottom. You see it has dimensions of 12, 567, 348. So these correspond to months of the year, the latitude axis, and then the longitude axis, 348. So I can add layer. You notice that QGIS did not ask me which month of the year specifically I wanted to visualize. So to select that, we go into the layer styling panel. By default, QGIS goes for a multi-bin color. In our case, what we want is a single bin instead. And now we already have something a lot more reasonable. So the way QGIS distinguishes between the months of the year is through this concept of band. You see here we have 1 to 12. So if we want the month of August, we just click on 8. The units are always indicated in the documentation, but those are micromoles per kilogram. So anywhere between 255 and 2400 in the month of August. And at this point, you have a typical raster layer. You can do everything that you're used to doing in QGIS. For example, you can add an extra layer on top. So let me grab a layer. In this example, it's the, oops. There you go. So the layer I just added on top of the alkalinity, those are the TMDL segments from the Chesapeake Bay program. So you see these different polygons that correspond to the segments of the Chesapeake Bay program. So by default, I just lost my alkalinity because the segments were defined on top of the alkalinity. But I can change this, replace the fill by an outline, change the thickness, of the outline. And then I get something reasonable, closer to what I was looking for, which is bottom alkalinity in August, the TMDL segments overlaid. And then as a bonus, I got the coastline indicated on top of the figure. So yeah, QGIS is one way to interact with the NetCDF archive. We can go back to the second example. This time it's in Python. So this example is looking at net calcification for Eastern Oyster in the Chesapeake Bay. So I had a simple equation for the net calcification rate as a function of the calcite saturation state at the bottom and as a function of temperature. So that's an equation that was provided by my colleagues, Émilie Rivet and Mark Brush at VIMS. Essentially, this net calcification rate, it depends a lot on whether you are on the left of this vertical dashed line or on the right. If you're on the left, you mostly have dissolution. If you're on the right, you have calcification. And the influence of temperature, you see here 5, 15, 25 degree. Essentially, what it does is amplify the rate, whether it's calcification or dissolution, it increases the rate. So the atlas includes calcite saturation state, it includes temperature, and that means that you can take this original equation and translate it into a geographical map for a different time of the year. So that's what I did in this Python script called calcification oysters, which is available on the website I mentioned earlier. So what it does, it basically translates it into map. In this case, one map for January, another one for September. When the color are warm, that means you have net calcification. When they are cold, that means you have net dissolution, which is mostly found inside the tributaries of the Chesapeake Bay. As I mentioned earlier, once you get into the warm month, all the rates are amplified, and so that's why you have the darker colors in the month of September. So we can take a look at this little Python script together. Right. So I tried to include as many comments as possible so that anybody can go back to the script and make sense of what it's doing at every line. Initially, you just load whichever library you will need for your calculation. And then in this portion, you see we are interacting with the atlas, reading the longitude, latitude, temperature, and calcite saturation state at the bottom. Next, we are reading the coastline of the Chesapeake Bay. We are reading them from a NetCDF file. This NetCDF file is available on the website. You can download it to recreate the figure by yourself if you want. The next section here is the calculation of the net calcification rate. So it's simply this equation here. And at this point, we are ready to create the figures. So we are creating two figures, the first one for the month of January, the second one for the month of September. And you see we're already at the end of the script at this point. There's a color bar that is being created. The units are being indicated on the color bar. In this portion, we are specifying the geographical extent of the figures. So the first two options is for representing the full extent of the atlas, but obviously you can focus on a smaller region. For example, here I'm providing the Elizabeth River if someone wanted to plot that specifically. And then that's it for the script. At this point, the command is simply to create the figure. So I can give it a try. Okay. So right now I have two figures on my screen. The one on the left is the month of January. The month on the right September, and we have our color scale. We see the cold colors represent dissolution inside the tributaries. And you can do whatever you want that you're used to doing in Python, for example, zooming on a specific regions of the Chesapeake Bay. For example, here it's the Elizabeth River. Once you zoom in, you start to see some blockiness. This is the limit of the resolution of the atlas. It's about equivalent to 600 meter by 600 meter, which gives you some information about the very coastal region. But obviously you can see where this resolution starts to fail when you're really close up on a specific region. All right. The next example is, this time it's in R, and it's looking at the seasonality of the carbonate system. More specifically, it's focusing on one monitoring station, WE 4.1, which is at the mouth of Mobjack Bay next to the York River. By the way, the figure on the left was created using the atlas. It uses the topography variable from the atlas. So you can recreate that. And it also uses the coastline that are available on the website I mentioned earlier. So in this example with R, what it does, it goes into the atlas, extract the seasonal cycle of alkalinity and DIC at this specific station, and then uses the CCarb package to calculate the full carbonate system based on the alkalinity and DIC. I'm doing it in R, but you could do it in Python using the PyCO2sys package. It works pretty much the same. So the script is carbonatechemistry.r. We can look at it together. Once again, lots of comments. You can look at it on your own time, and hopefully it will all make sense. But it's always the same gymnastics. You load your library, then start to read your variables from the atlas, in that case, longitude, latitude, salinity, temperature, DIC, TA. Next, here I'm defining the longitude and the latitude of the monitoring station, right there. And then the next step is to take the information from the atlas that is defined on this latitude-longitude grid and interpolate it spatially at the location of the station. There are multiple ways to do this. Here I chose to just do a bilinear interpolation. So it's just a simple spatial interpolation. And once you interpolate in one location, what you will be left with will be time series. So 12 values representing the months of the year. So that's what's happening here. You see you have a for loop over the month of the year, 1 to 12. And you're calculating time series for salinity, temperature, DIC, and alkalinity at the location of the station. Once you have your time series, you are ready to use CCarb. So in this case, I am calling the carb function, and I have all the input to the function with lots of little comments explaining why I make certain choices. And once again, the input I'm giving to the CCarb package is alkalinity, DIC, salinity, and temperature. And then in return, CCarb calculates everything else. Next, what I included is to create two figures in R. The first one shows TA and DIC over the months of the year. So that's what we're seeing here. It starts with TA on the left axis, then I customize the horizontal axis with the month of the year, and then I add DIC on the right axis of the same figure. So we can see what it looks like. This is the result on the right, alkalinity in blue, DIC in red, and as a function of the month of the year. There's a huge depression around March, April, May, which corresponds to the wetter months of the year with the influence of the river that tends to depress both TA and DIC. And then during the drier months of the year, you have much higher values. TA is close to being conservative, while DIC has additional complications due to sinks and sources of the biology. So that was the first figure in the script. I included a second figure starting here. And what this second figure shows is the saturation state on the left axis and then PCO2 on the right axis. So we can see what it looks like. So calcite saturation state in blue, it has values between 2 and 3 over the seasonal cycle. So the values are substantially above 1, which suggests that we have good calcification inside Mobjack Bay. Then we have PCO2 in red, anywhere between 300 and 500, depending on the time of the year. You remember that the atlas is representative of 1985-2023. So atmospheric concentration during those years was roughly 350 microatmospheres, so about there. So when you're above, you're having outgassing. When you're below that line, you are having ingassing. So next in the script, I decide to have a little bit of fun. I asked the question, how much of this seasonality is related to the direct influence of temperature, right? How much of these bumps is due to temperature itself? So the way I answer this question is I go back to my time series of temperature here, and I replace the original value with an annual average of water temperature. And then I recalculate the carbonate system with this annually averaged temperature. By doing that, I'm taking away the influence of temperature on the seasonal cycle. And once you do that, you get this figure. So the blue, the calcite saturation state barely changed, meaning that temperature has a minimal direct influence on the saturation state. But PCO2 is drastically different. Once we took out the warm summer months, basically we lost the high bump during the summer period. And now the seasonality is close to being reversed just because we took out the influence of temperature. So that's the carbonatechemistry.R script. The next example I had was in R, and I'm looking at the habitat suitability for sandbar shark. So it's a species that uses the Chesapeake Bay as a nursery during the summer period. And there was this paper in 2020 that described the habitat preference of sandbar shark as a function of salinity, dissolved oxygen, and temperature. So all of these variables are available in the atlas. So it becomes possible to translate these GAM functions into actual map of where you expect to see sandbar shark according to its preference. So that's the script suitability sandbarshark.r. And we can look at it together. At this point, it probably looks very repetitive. Once again, you read the variables you need, salinity, temperature, and oxygen at the bottom. Next, I included the GAM function from the Creer et al. 2020 paper. They are included as CSV files, so text files. They are available on the website if you want to download them and recreate the example on your side. The original GAM were restricted to a certain range of environmental conditions. And so in this portion of the script, what I'm doing is I'm slightly extending this range of environmental conditions so that the GAM have plausible values throughout the possibilities of temperature, salinity, and oxygen. And at this point, we are ready to use the information from the atlas to calculate actual maps of where the conditions are suitable for sandbar shark, which is what I'm doing here using the approx function from R. And then I defined the Habitat Suitability Index, HSI, as the multiplication of the preference for oxygen, salinity, and temperature. So when HSI is close to 1, that means that all three criteria are satisfied. It is pleased with the oxygen, salinity, and temperature. If it's 0, then it's really one of the three, or the three are unsuitable for sandbar shark. And at this point, we're ready to create a figure. I decided to focus on the month of August 8. And then it's just a matter of creating the figure using R. So I define a color scale from 0 to 1 by increments of 0.01. I select a specific color palette. I define the geographical extent of the map. And then I ask R to create the map itself. So if we give it a try, at this point, R created a figure. We can look at it. There you go. This is the figure that R just created. It's the map of the Chesapeake Bay, the whole geographical extent of the atlas, a color scale between 0 and 1, where 1 means that sandbar shark is perfectly pleased with the conditions. And we see that for the month of August, specifically, sandbar shark would favor the southern portion of the Chesapeake Bay. All right. Moving on to the next example of usage, I wanted to showcase the fact that the atlas, by being defined on a very simple grid of latitude and longitude, it becomes really trivial to interpolate the conditions from the atlas upon an arbitrary location within the Chesapeake Bay. And one way to do that is to define transects. So in this figure here, I have 5 transects, one for the main stem of the bay, the York, the Rappahannock, the Potomac, and the Patuxent. And the idea in this Matlab script here is that we just take the results from the atlas, interpolate them along this transect, and that gives us these representation like we see on the right. So this particular figure is showing total alkalinity in the month of August along the base main stem. So that's the dark red transect shown in the figure. You may ask yourself, why is this transect going up and down along the main stem? The reason is when I was defining this transect, I was trying really hard to go through the most important monitoring stations that are aligned along the main stem. And if there was no monitoring station in a specific portion, I was rather favor the deepest portion of the main stem. So I will follow the talweg of the Chesapeake Bay. And I did the same thing for all those tributaries. I tend to follow monitoring stations as well as the deepest location within the tributary. So the horizontal axis of those transects is distance from mouth in kilometer. So in this case, it's the distance from this point here. And sometimes distance from mouth can be a little abstract. So I decided to additionally have some labels for the latitude along the transect. And so you see it goes from 37 degrees north up to 39.5, which would be about Havre de Grace in Maryland. So the vertical axis is depth. And then the atlas has information for the surface and the bottom. And I'm representing this information as colored circles that are tied to the color map on the right. So the minimum and the maximum of the color scale correspond to the minimum and the maximum encountered along this transect. So we can look at the Matlab script that was used to create this figure. Here we're reading longitude, latitude, as well as topography. Then we are selecting the month of August. That's completely arbitrary. I just picked that one. And then I decided to plot alkalinity at the bottom and at the surface. It could have been any other variable of the atlas. Once again, that's completely arbitrary. Feel free to change this. Next, we read the coastline of the Chesapeake Bay. It's the same NetCDF file I was describing earlier. And then we have a new NetCDF file here. And it's called longitude, latitude, transect. So this is the NetCDF file that contains the actual information about where those transects are positioned within the Chesapeake Bay. This NetCDF file is available on the website I was mentioning earlier. You can download it. And we see that it has a total of 5 transects that are predefined: the main stem, York, Potomac, Patuxent, Rappahannock. And obviously, you're free to define your own transect if you happen to be studying a different tributary. This block of code here is simply creating the earlier map of the Chesapeake Bay with the 5 tributaries. That's all what it's doing. And then we come to the meat of the script. First, we decide to focus on one of the 5 tributaries. So you simply uncomment whichever of the 5 transects you want to focus on. And then this is where the spatial interpolation is taking place. So remember that all the information from the atlas is defined on this longitude, latitude grid. And it's just one line to extract this information from the atlas and interpolate it over the longitude and the latitude of the transect. So very simple, just one line and it's done. So we're doing this 3 times. First for the bathymetry, since we're representing the bottom of the transect, and then we are doing it for the values of our variable we chose at the bottom and at the surface. Next, here I'm defining a polygon in gray that will be representing the topography at the bottom of the transect. So that's the gray that you're seeing in the transect, that's a polygon. And that's where I'm defining the polygon. Next, I define the minimum and the maximum values for the color scale, which just corresponds to whichever values we find along the transect that we just created. And then we're ready to create a figure. So here the patch command is creating the gray topography at the bottom. And then we start to overlay additional information on the figure. So there's a for loop that is going through every point along the transect. And each time what it's doing, it is adding a circle at the location that we are right now. And in this case, close to the bottom at 90% of the total depth at this location. So the circle is then colored by defining a red, green, blue code. So that here we're simply interpolating the color scale according to the current value of alkalinity at this point. And then we are giving this color to the circle. And at that point, we just repeat the same thing for the surface circles. And the figure is pretty much completed at this point. We just call a color bar, add a color bar, and then we add the labels for longitude or latitude along the transect, depending whether this transect is mostly north to south or east to west. So the script takes that into account here and adds the little labels at the bottom of the figure. So I have a couple of examples here. That's bottom alkalinity along the basement's main stem. This one is the same thing, TA, along the Patuxent River. And in general, alkalinity will be decreasing as you move inland. So you get this very strong gradient going inland. But interestingly, once you arrive at the Potomac River, the gradient reverses because you have very large alkalinity values flowing down from the upstream portion of the river. And so that creates this reverse gradient as you move into the northern portion of the Potomac. This figure is the Rappahannock River, so the more classical gradient decreasing values as you move inland. And finally, the transect along the York River. So all of this is inside the script and it's available on the website. So I'm repeating the address. It's nordet.net/MACAN 2024. The slides, the scripts, the NetCDF file, it's all there. I'm here available to answer any question you may have about the atlas. But if you prefer, if you're shy like me, you can also email me. That's fine. And it's possible for me to create new versions of the atlas over time. So if you have suggestions of what to improve, what to modify, what would be really cool to add, just shoot me an email and let me know. And I would like to thank Kirsten and Janet for hosting the webinar, and Alexandra and Erica for suggesting this webinar. So thank you very much.
Thanks, Pierre. That was an excellent dive into the power of the digital atlas, and really appreciate seeing the examples of how it's being used to look at net calcification rates and seasonality of carbonate chemistry and all the things that MACAN's talking about with all of our stakeholders too. So really appreciate that, and really appreciate the resources that you've provided for us to explore on our own too. We do have a couple of questions, and if there are any more, please go ahead and drop them in the chat or in the Q&A box as well. One of the questions I think is the atlas that you've created is a very recent product. Do you have any examples of how the results have been or are being applied for management? Are there any of the maps that have been used for like state of the ecosystem reports, or are they going out to managers right now, or is this still kind of your vision?
I'm not aware that it's being used at the moment for a management decision or these things, but you're right to point out that it's fairly recent that it became available. And I think I'm still in the process of telling people, hey, it's available, feel free to use it, see what you can do with it. So I think we're still in this loop right now. I presented the atlas at Chess CRS and at this webinar, but otherwise I haven't done anything to contact people and say, hey, this is available. So there's still a lot to do on that part.
Okay, well, hopefully this helps get the word out on that and then. Yeah, and then I guess the other question that came up is you mentioned about updating the atlas. Are there plans right now? It's through 2023. Are there plans to do like another 5-year iteration, or is there for updates?
Yeah, so it's based on a model and we make improvements on it like every month. So it's a constant work in progress and things always get better. They don't get worse. And yes, I totally plan to create additional versions. And what's really nice with this CNO repository is you don't have to create a new DOI or anything like that. You just send your new files and say, hey, this is an update. And the same DOI link remains available, and you will see that there's a new version available, and nothing more complicated than that. And it's free, so it's nice.
That's great. It's always great to have a free resource too. All right. Well, I think that's all the questions we had for today. So really, again, thank you so much for sharing your time and sharing these great resources that you're developing. We're really excited to see them and hopefully share them a little more broadly. To that end, we will be posting the recording on our website at midacan.org. So anybody, spread the word, share that link with people too once it's posted. And we hope everyone will join us for our next webinar in November, featuring some of the work of our MACAN fellows. And as always, if you have other questions about MACAN, you can email us at info@midacan.org. And we look forward to seeing you soon. Thanks so much.
Thank you.
Bye-bye.